Hey guys, how's it going back again? So here we are for another round of Open-FDD, some vibe code project on the building 100. It's called the Liberty Building, Building 100, and it's in the upper Midwest of the US. Very warm, humid climate in the summertime like it is right now, um, and also very cold in the heating season. At the moment, we're getting a ton of wildfire smoke from Canada and then western Minnesota. So and it's even drifting down way further than I've ever seen it before. So it's not too common if you live by the Canadian border, but if yeah, it's even drifting down hundreds of miles. Kind of crazy, crazy times. I think and everywhere in the world, there's some kind of like crazy weather events, everywhere. So it's almost unavoidable. Anyways, let's keep on continuing on with this building 100 at the moment. Yeah, about these wildfires. I can look out my window and it looks like just like smoke everywhere. I've never seen this before, but yet these wildfires are hundreds, if not 1,000 miles away or something. Yeah, just you can even smell it. It's like a campfire in your building, in your house. Your eyes burn and everything, but the fire is way far away. So, um, yeah, I guess if you live in my section of the world, besides it being like very cold and boring in the winter, in extreme winter events, we do have to worry about this kind of crap every once in a while. So I know everywhere it's like hurricanes, tornadoes, flooding. It's everyone gets their fair dose of whatever nature throws at you. So some of the stuff we're trying to do in the fault detection world in HVAC systems, I feel like it is kind of like intertwined with everything that Mother Nature throws at you. So during these mild times of the year, really trying to optimize economizing free cooling, and then times of the year that it's really hot, that's when we would pay attention to optimizing uh, cooling systems, chiller plants, air handling unit systems, and then in the heating season, that's when we would be optimizing heating plants, obviously. Um, and I kind of like to break it down into seasonal, really looking at on a per season basis. I think it's kind of probably pretty common for people in retro commissioning to kind of design projects. I've seen really good projects designed where they're uh, each season is evaluated independently rather than someone randomly just designing some project, and by the time it hits the ground, who knows which season it'll even be or if it'll even be applicable to the systems in the building. So you kind of have to keep that in mind like when you're timelining things, is like you um you want to, if it's a school, you want to critically look at when the school is populated during the occupant times of the year, that kind of thing. um I think for this building 100 too, like this learning that this building was built in the 80s. So in the 80s, variable frequency drives were brand new. We're still installing pneumatic controls, so there could be many different generations of direct digital controls which have been significant modifications since the 80s. It started in the 80s. Um, so this building apparently does have some pneumatics still. Um, I think I can probably show this. Let me just see if I can get back to this. Let me see if I can just find some image here, just of like an artist's rendering of like what these glass buildings look like. Um, so kind of like picture it like two pretty decent size. These are considered large office buildings. I think the people that do like energy modeling and design, like small offices up to 50,000 square feet or something like that. Medium size would be 100,000 square feet, and then I think large offices are 150,000 square foot range, which both of these are 150,000 square feet, I think, and 6 floors. I think I do have some blueprint drawings. There's no mechanical schedules. So I don't know how big these air handling units are, but we talked about it yesterday, and I showed some screenshots that there's 2 air handling units, and I think they're monsters. Like they would have like close to 100 horsepower fans, and buildings with high amount of glass like these would be, there's I know some people like from previous experience that have HVAC design backgrounds, so I'm kind of going off of some like very high level benchmarking based on uh, ASHRAE zones and amount of square feet, amount of glazing, just like very rough guess size of chillers and size of air handling unit fans that could be pushing air around the building. Because I think that we could get into like there could be like a project designed to totally retrofit the building to DDC, all VAV boxes. I would think like a building like this, 2 big air handling units, could have somewhere around 100 VAV boxes. Just throwing that out there, spitballing it, or more. Um, and yeah, each one of these buildings, there's 2 twin buildings. They're both identical, both similar systems, and like we haven't even touched the other one yet. Um, and I think I see some optimization that if the building was totally cut over to VAV and not pneumatic VAVs, I think there might be pneumatic zones. I still have to confirm that. But back in the olden days, before direct digital electronic controls, everything ran off of air pressure. They're called analog controls. So uh, compressed air controlled a bladder to put like a bladder that was like the air damper to modulate the amount of air that goes into a space. Somehow they would even calibrate those for um, like modern DDC systems. VAV boxes get calibrated by test and balance contractors with flow hoods, and they dial it in with like a little wheel thing. And back in the day, they would do all that with air pressure gauges and dial in the volume of air into the zone. All ran off of air pressure somehow. It's kind of like a dying art that the people that installed those, um, they're probably all retired by now. I've had to repair pneumatics before, were multi-year projects that still school districts, multi-year school district projects that were called to cut over half the building and leave half the pneumatics going for the next year is a real nightmare. Um, so there are still some pneumatics in the building, and the idea would be that I think there's some optimization not only in we should just I'll dial into the app in a second, but like the energy saving strategy would be um, costs that it would take to completely cut over the building to DDC. And then perhaps there's like an ROI that we can calculate. Um, Big fans in doing guideline 36 for duct static pressure reset and temperature reset, and also uh, when they would cut all of this over, things would get balanced and by test and balance contractor, and that is in the time frame too where test and balance contractor would validate that these big old monster air handling units can still um, push air around the building as expected. So let's just look at that again too. Um, so two monsters inside the building. They don't look like big units, but I think in reality these would be close to 100 horsepower fans. I think, just based on the size of the building, 2 of these units only existing in the buildings. I think if it was a modern building, you would see one on each floor. Um, but apparently there's 2 of these big, just calling them beasts. So like, and at the moment the duct static pressure is fixed, 1.65 inches water column, And these big fans, just the supply fan maintains this duct static pressure sensor, um, which would just be somewhere in the building, usually 2/3 around the down the duct stream. Big air handling unit, probably pushing multiple floors. So it's maintaining that duct static pressure, and then most likely this return fan is just doing a speed offset of this guy. Sometimes there are um, guideline 36, or sometimes like they even put airflow measuring stations on these fans, or even some of it's even like mixed air pressure control. But usually the simplest way to do it is there's just this guy is controlling to maintain that duct pressure, and then this return fan just does a fixed speed opposite off of that. Usually it's just like 10% less. They just throw that in there. But I don't think that that sequence meets energy code anymore. Like that was just a really old way of doing things, and it works. It probably works totally fine. But I think that there's, I have to confirm this, but modern energy code requirements, that's against code requirements to do a return and supply fan speed offset. I think I should confirm that. Even though it works really solid and I've set it up many times, I'm pretty sure that return fan speed control is different. So like the idea would be that um, this, if I was, hoping to do this. This is my goal: is to design this project with the help of fault detection. We can see that some of these energy savings strategies, we could do a guideline 36 duct static pressure reset on the supply fan, and then also when we would cut over the project and these big monsters would be left in place, that the test and balance contractor would also validate that these fans push design airflows through the building. And then you would also redesign ventilation rates to like bring the building up to code, basically. I'd have to check too. There might even be something that could be done on the like airflow measuring stations here, where basically if the entire building is direct digital control, we might even be able to do more demand control strategies, even put like CO2 sensors in the zones. I should check with some people that are still in design, doing design work, what would be the latest and greatest thing to cut over like a VAV system like this. I want to do the duct static pressure reset. I'm hoping to calculate all this too, so we can do like some energy savings calculations, and then maybe even spitball investment return, and maybe even give the client, this would be your energy savings project. Return on investment is this, and then we would want to see if it's compatible with their local utility rebate program, and maybe that could even help improve the investment return too. That's where I'm going with this project. I wasn't originally intended to march all the way down this path, but it's kind of going this way. So thanks for bearing with me for so long. It's yeah, that's where I'm seeing the energy saving strategies is guideline 36, duct static pressure control, discharge air temperature reset. And to do all that, we need a fully functional 100% removal of the pneumatic system. And we can talk about that more in the future. And then I think this these chillers would be decent sized air cooled chillers too. That this enable set point is also something that we could bump up to 60. I'm dying to know like if when the maintenance department, when they run this building, like we've talked about before, if someone had to modify this discharge air temperature set point down to 50. Usually the design cooling leaving air temperature of the air handling unit is always 55. And then you float that up in the winter. But they do that for dehumidification for design of 55 degrees. And then someone had to lower that down to 50, more than likely, because there was probably a very large building full of glass, and there's probably some portion of the building that is not cooling properly. And then when the problem is when these set points are left in place to operate like that year round, probably because it was just peak summertime conditions, then wasted energy. There's a ton of wasted energy in that. Then the ideal thing to do would be during the shoulder season. That is where we could do Guideline 36. They do have some like really neat things of like being able to reset air handling unit temperature and pressure based off of demand. So like you're looking at VAV box airflows, air damper positions, zone temperature and set point deviations, and then we can implement an algorithm on the air handling unit, and it works pretty good. So that's the strategies. And there is typically some. I have also been on a couple research projects. This makes me think of this right now. I'm just going to show this is my old employer named Slipstream. I have to do a little bit of, but this is basically a technical report for implementing Guideline 36. So I'll have to read this because this contains the basically this old school was pneumatics, and it cost a certain amount of money to upgrade the building completely to DDC, and then they removed the air compressor completely. And then yes, so it was actually simple payback was less than 7 years. I think the final calculated numbers was exactly what you would expect for a Guideline 36 project. A couple big old air handlers that would serve multiple wings of the school, some old boilers in this, all existing pneumatics, and we were able to completely disconnect the power from these guys. A couple cooling valves need to be converted to digital. Really old, kind of similar setups to this system too. And then this was actually the panel of this air handling unit. It's hard to see, but this is actually, I think this right here. My little mouse highlighter isn't working. But at the bottom of this panel, by these analog gauges, this is actually like a really old KMC controller right here, where it's just a board, electronic board, that would control this air handler. Really old KMC stuff. And then that ended up getting, there was inlet guide vanes on the air handling unit. So even before VFDs. Long story short is that this got updated with latest and greatest Schneider Electric. Everything went to digital. And let me just scroll down here. Kind of pretty similar to like what I'm doing in the here on this Open-FDD project is not too terribly different than this Guideline 36 research project. It's kind of like the same approach. It just happens to be something I'm just thinking about in real time. We were able to reduce the run hours of the equipment. Okay, so then this is some of the energy saving strategies. Avoided energy use. I remember it being pretty close to like what was expected on a Guideline 36 project for a simple ROI. Um, so let me see if I can find that real quick. Simple payback. Well, I guess it was calculated to be 13 years. So maybe this is something that we can go off of. I'm hoping to do some savings calculations in a little bit more sophisticated than this, but to do so this was actually um, measured savings. So I don't think there was much done for initial savings, just very rough estimates. And then we actually did the savings calculations, sub-metered everything. Um, and what I'm hoping to do next is actually see if we can use Energy Plus with some data from the Open-FDD 519 project and see if we can calibrate a model. And just to see if we could come up with something perhaps even close to this, I guess that's 13 years. So I thought it was better than that for some reason, but I will look at this again. It's been a little while since um, this was fully upgraded, but yeah, this is a cool project. I love this stuff. So I also have some Guideline 36 Niagara widgets too. I showed them before on different former videos, but they're pre-built wire sheets for Guideline 36. And this building is a Niagara platform, so it could be something to make projects cheaper and easier. That the algorithm is built already, and then the field technicians just have to go and basically link it all together. But what's really important is that the building absolutely positively requires 100% DDC um, to make that work. Okay, so let's see if we can um, check the latest and greatest updates of 519 project. Okay, so like right now I'm on Open-FDD, join the Discord server. With that button, I just want to see if the docs are updated. So I have been updating the rule cookbook. We're still using pandas. See if we have any updates here. Okay, so we do have we are have some updates here for this sensor validation sweep. On this project, I'm not really paying too close attention to this, but these are just this is actually the function buried into the Vibe 19 application that sensor out of range, hard range. So pressure, humidity, temperature, flatline sensor, spike, so sensor rate of change, which we do have some few differences for humidity and pressure. Stale data. Lots of stale data on this data I have, unfortunately. Context aware sensor rate of change. And when I'm doing this Open-FDD stuff, I'm just kind of briefly just glossing over this, not really diving too deep into the a little bit, but it's not the main thing I'm looking for. PID hunting. We have a PID hunting one too. So so this is like how we're calculating PID hunting. I feel like my little mouse thing isn't being on me, so let's get you going. So, okay, there we go. So control sweep. So this is anything that's an analog output, usually as some kind of a PID or PI control or just proportional control. And what we're doing on the back end in pandas is a rolling 1 hour total variation of any 0 to 100% control output for dampers, valve, fan, or pump speeds with a span greater than 20%. So like what we're doing in this, in a simplistic way, is through the course of an hour, is like we're adding all of, so like the control output is going like this constantly, and we're adding all of those peaks and valleys together. And then we're coming up with a total travel threshold in percent per hour, to be in the range of 5 to 2,000%. If anyone has a better way of doing this, I'm like really curious to see how you're doing it, but this is just something that we should play around with. So this should be a tunable slider on the web app front end where we could, we should find an output that's hunting quite a bit and then, validate it. Okay, so we have lots of air handling unit stuff. So this is getting updated nicely. I just wanted to prove that these docs are continuously getting updated with the equations. Anything with the FC, that is guideline 36, guideline 36 equation. This is actually the PID hunting for entire air handling unit system. Where if the air handling unit is oscillating in and out of heating, economizing only, economizing plus mechanical, and mechanical cooling mode, all based off of valve positions. So like we're running data through these functions, and it's the function is telling us that there's hunting occurring on here by how often the air handling unit is oscillating between these different modes. It's all defined by guideline 36. So there's a lot that you can tell by heating valve, cooling valve, fan speed command, and the outside air damper. As they're kind of going like this, those are different modes that the air handling unit would be operating in. And guideline 36 defines stage changes of 5. I think it's actually 7, but that seems like an awful lot to me as the maximum state changes per hour. It should only be like 1 or 2, I think. Another way to get hunting. So like another thing that I really want to dial in today is on the latest update of 5.19, since we're kind of really looking carefully at economizing, because this data set is for a shoulder season. So we're kind of like zeroed into this shoulder season where we have the point of like end of the heating season, barely get to see the little bit of the boilers come on. Great view of the entire shoulder season, and then just up to the point of the beginning of July, where that's right when the hot weather, usually the hot weather starts in June, but so we kind of get that full stretch. And what I want to really zero in here is I thought yesterday that that these let's see, where's our pictures of our air handling unit? New backup. So I thought yesterday that these weren't opening at all. And I kind of walked back on that at the end of the video, that these economizing dampers weren't open at all. And it's actually a point that was mapped wrong by AI. So like using AI to put we've talked about this before, it's the data model in HVAC. So it's mapping CSV file columns to HVAC names, and then that maps automatically to fault detection equations. So it's the fault detection equation is based all on HVAC naming, and then AI maps the raw messy data name to the function, and it mapped the wrong point. So that's why we were seeing this as constantly a value of 100. Yeah, completely wrong. So AI screws up. Okay, so I just wanted to show you this. So like some of these, so these fault detection equations for economizing, I want to dial in a little closer. So fault condition 8, fault condition 9. These are, look at the economizers pretty closely. Maybe I'll just keep the page open to here. One for mechanical cooling only. But basically these fault equations, it looks for the outside air dampers open. Chilled water is greater than 10%. And there's, this is like an outside air temperature minus a mixing tolerance is greater than the supplier's set point minus a half degree plus a mixing tolerance. So it's kind of all defined by guideline 36. So like we'll check it out and like see what I think that this passes. And what I wanted to look at more closely was this AHU economizer damper open, chilled water valve open, and then that these supply air and mixed air temperatures track each other within some sort of a tolerance. And then there's also another economizing one further down here too that we should look at. Okay, so like let's get back track. I'm gonna go into the vibe code app 19. I'm also started some kind of concept idea of debating if this is worth showing you guys or not right now, but okay, so let's go in here and then I'll just update the Docker containers real quick. So we can go down here, go down to the same steps by hand. Stupid little mouse thing is screwed up again. Mouse highlighter. Okay, so this is going to pull Docker containers. I have, I'm SSH'd into my little Linux server on my desktop, which you can use a Raspberry Pi, you can use anything. You could even use Docker Desktop right on your host computer. I just think this is more fun. So I've already updated this a few times for some bugs. So this is just going to do a Docker pull from the GitHub container repository for the Vibe 19 latest, which is also getting dumped into Open-FDD. I've mentioned this a few times, is that I'm converting this application slowly over to a more production code base written in Rust. So it's coming. It might be like a while, month or two, who knows, before I can show you this. But this will get like this Streamlit application will be converted from a data science dashboard to a full-blown web application as well. Okay, so we downloaded the latest image. Okay, so I just want to show you this just real quick. This vibe code app 20. So this will be something I am playing around with the output of this to use Energy Plus. I think there's other projects, one called BOP Test. That's another one too. It's a full-blown Docker container with a physics-driven energy simulator inside of it. And then the Department of Energy also has Energy Plus. So it's free software to do energy modeling, even Docker container driven. So like we took this yesterday is Docker NREL Energy Plus. So NREL maintains Energy Plus. And they update it quite a bit. So this is published to Docker Hub. And then, like I was explaining yesterday, like Vibe 19 is published to GitHub, to the GitHub container repository. That's what GHCR stands for. So NREL publishes their containers to Docker Hub. And then what I am playing around with is G plus model context server. So this is coming. This here's Eric Martin. So LB&L made Energy Plus MCP. So this is coming where what I'm hoping to do is for this Liberty building. I'm slowly getting utility records from the client. We would be able to create an energy model of the Liberty building with some assumptions. So there will be some lick your finger, put it in the air um, type of a model that with the help of AI. So this is what I'm really hoping to leverage AI agents to. I was originally hoping that we could do it right into the uh, Vibe Code 19 application, but I'm just finding it like I can't trust I feel like I just need like my own eyes to like look at the fault detection outputs and the equations. Um, but what I'm really hoping to do is really leverage the data that's output from that to be a calibrated energy model. So that's where I'm going. And then like with the ECMs that we flagged with the fault detection outputs for the guideline 36. I'm really curious, this is coming, that if I get enough data, utility records to see how close AI can model this building, and it might be really kind of people that specialize in this know way more than Energy Plus than I do. Like I know just enough to be dangerous. It's not my specialty. Um, but for some people it is. And if I can kind of uh, prototype a concept idea that we can get enough data from Open-FDD, AI can calibrate a model. There could even be projects where this is a specialized person hired for the project. Um, there are people, Slipstream, where I used to work, had a couple engineers that was their bread and butter is Energy Plus and modeling. Very common in the consulting engineer world that there's a person that they have some master's degree in engineering and this is what they're studied in their graduate courses. And they're the people that are like, um, if I ever was paid for to do this professionally, I would probably find one of those guys or gals to put their review the output of the calibrated model, and yeah, so that's where I'm going with this. Um, the fault detection person, which I'm filling those roles at the moment, could be one person on the project, and then energy modeling person, um, and then yeah, people kind of reviewing that work. Okay, so this is coming. It's coming down the road. So it might not happen today or tomorrow, but this is like baby steps here. So, um, okay, so I'll be doing this on the side. It's just like slowly updating this fault detection report and, trying to make the tool that it can output enough useful data of like um, that we could feed into Energy Plus, like actual weather data, um, fuel use per month, actual utility bills, and then actual runtime analytics of the equipment. So we could see, we'll look at that now, but like the runtime analytics of the air handling unit would be like, what does the air handling unit maintain for duct static pressure? What does when does equipment start and stop? How many run hours per week? Averaged supplier temperature, in certain conditions. So like we can like really try and document through the Open-FDD tool, Vibe 19, that it's through analytics, which is just like summarizing through statistics, like how the equipment operates over time, and then be able to hook that into like an energy model. Okay, so like let's just jump right to it. Okay, so this is the latest and greatest. Little triathlon guy up there is. Let's get him swimming hard. Okay, so I have this zip file with weather data packaged in it already. And there is, if you just point, so I'm just going to go back into here, into the Vibe 19 project. And if you just point your AI agents at this markdown file, ChatGPT or Claude or Cursor or whatever, not only is it how to build this application, which I'm fully taking advantage of for my Open-FDD project, but others should as well. There is okay, so like we do a HVAC mapping context for agents. So this is how to pre-process the app. So the AI agent just kind of loops through your CSV files, and then um, it'll make this JSON file and stick it in there. And then when we upload that to the Vibe Code 19 application, it looks for that. It parses that JSON file in the backend Python code, starts crunching numbers in the pandas computing library. So, okay, so we're up to 59 rules. Okay, so I constantly have to like set this. There is a feature here as well for saving the state of this application, where I haven't tested that yet, but it's another thing too, where if you have a project and you're going back to it over and over, like I am, that you'll be able to like save this config file. So this is, I'm just re-inputting the schedule for the building. So this is the schedule that the owner is required per leasing agreement that they keep the building conditioned from these hours to these hours. And then it's up to us in HVAC optimization to put algorithms in place that bare minimally run the building beyond this. So like part of the strategies too is like the building automation system would be a perfect mimic of this Monday through Friday, the schedule for the leasing agreements, the 72 degrees Fahrenheit requirement, and that we would have optimal start algorithms that if equipment needs to run earlier, it can. Okay, we've talked about this 100 times. This is, we're kind of keeping this, we're keeping track of how much more time equipment runs than it has to. This mechanical cooling, so this will be part of our ECMs too. We do have a little bit of deviation in between the web weather. So this is what we talked about on the last chat a bit. So you can zoom in. These are plotly charts. So this is data from OpenMedio, where we're looking at the deviation of the web weather to local outside air temp sensor, where it's not bad. I think this is kind of cool actually. And hey, looks like we have a fault right here. So like at the local BIS sensor, reads on average warmer than the web weather. So some people are biased on this. Like, I would rather trust the airport weather station at the local airport than the flimsy $20 sensor installed on side of the building. Um, just the assumption that the airport stations are calibrated, I hope, and that never ever ever happens in building automation. I've never once ever seen a sensors. Rarely are they calibrated; they're replaced. Um, and then if they're calibrated, there's usually kind of a wonky offset that they do in the programming tool, where they'll just plus 2 degrees or minus 2 degrees or whatever the offset is. So it's never perfect. The calibration is, when it comes to calibrating sensors and building automation, I think is kind of a joke a little bit, because there's only a fixed offset that the technician can do with a product line that they buy from the manufacturer. And as you can see, like, these are changing constantly. It's never fixed. Look, like even here, that the sun might be shining on the sensor. These might be clouds. Who knows? Um, okay, I think we even had a histogram of the outside air versus web, but whatever. Okay, so this is another thing I wanted to show you guys to, which is what I found out late in the day yesterday, um, that this MAD-C might be hard to see. That's the mixed air damper command, 0 to 100%. So this is the economizing damper. And as you can see, there's lots of squiggly lines, so it's economizing, which is good. So that's what we have to change this in the data model, and I wanted to show you how you do that manually. Let's go back. Let's reset the accesses. Okay, so this is probably hard to see from where you guys are, but like, um, you can kind of see like a general trend in the data that we started at the end of heating season, and then we're in full mechanical cooling season, and like this, it's a very 0 to 20%, 0 to 20%, a little teeny dip of economizing right there. But then in the middle, so this would be March, April, May, June. We start seeing this hot weather, which we would expect to see. And like we're almost at just minimum position. So that's good. So that's a very nice thing to view. Supply fan speeds. Another thing, like, I think there's a problem with this building that we could include, as an as a energy saving strategy. The other air handling unit, I think, had something really odd in the static pressure data. Okay, so little triathlon guys there doing his thing. To wrap this up as soon as I can. This stuff takes time though. Like, the more you drill into it, the more time it takes to really put a good effort forth, I think. Um, okay, so the DAP underscore inch water column INWC. So this something is going really here, where I notified the client that there is something really off. And so like this 7 inches water column, that is a ton of static pressure, where usually like the duct systems, um, might not be rated for much more, where you could be uh, really stressing the ductwork. So that's something I also see really odd. Okay, so like I want to just go, let's go, oh shoot. Okay, so like let's go to the data model tab. Um, Data model tab. This app is kind of clunky and it's really slow because it's just a um, data science dashboarding tool. So it's kind of has a little bit of some uh, wonkiness. It's laggy, it's slow, but I think it's something that could be optimized in time. Okay, so like do have some VAVs here, but okay, so this is advanced down here in the bottom. And then I am selected for air handling unit 1 and see my outside air damper. The AI mapped the wrong point to it. So MAD-C. So we have to change this. And went to gray. So it's thinking. And then I also have to change this to air handling unit 2. And then we can go rerun all of our faults. And then before this video gets too daunting, I just want to look at study those economizer faults, and then maybe try and zero in a little bit on the this air handling unit 2 with the sensor reading about 5 times higher than what it should be in static pressure. Zero in on that part too. Okay, so let's go. No, air handling unit 2. So I just have to remap this. Yeah, so the AI mapped outside air damper command to exhaust damper position fan enable panel. It's way off. So AI makes mistakes, but it's super useful in doing things like this, I think. And it's kind of nice that this tool has like nice easy way to fix it if there's something really wrong in the data. Okay, so rules, just click on the rules button. Run all 59. I should really make the little triathlon guy start doing an Ironman. Oop, it's pretty fast. Ran 59 evaluations. Let's go back into FDD plots. Like I said, I'm not going to look very hard on some of those like sensor range, sensor changes per hour per HVAC type. I don't think I'm going to like study those too in depth, just kind of gloss it over like once. Um, but like the thing that I'm really after is this really mapping out the heck of like running the chiller below 55 degrees Fahrenheit and then economizing. So this economizing fault equation 8, and then some of this like duct static stuff. It looks really off to me. Okay, so like you can view like analytics just by each little drop down here. So this is sensor fault, sensor range. I'm not going to look at it very hard. I kind of mostly looked at the time series data. Pit hunting, so duct static pressure, we do see some faults. And this is a good one too, because like with these fans being um, monsters, like really big fans, when those fans go up to 100%, there's a lot of power being pushed through those. And with the fan laws, it's a cubic relationship too. So like if you can trim back fan speed just the teeniest bit, it has a cubic relationship for electrical power consumption. Um, So we do have some faults here. Let's see, where was that? Fault hours, 70 hours. 70 hours of time this 100 horsepower fan ran wide open because it's not able to make its static set point for some unknown reason. I think this was due to the, we talked about this briefly, is that the chiller and the air handling units are on schedules. So like chiller shuts down before air handling unit does, and air handling unit needs cooling, and when it doesn't have cooling, that's when VAV boxes start opening up. Duct side pressure goes down in the system, and before you know it, these fans are running wide open. So this is an energy savings opportunity here too. I think like the fix that I've seen for this is we start the chiller based off of purely based off of cooling valve position. So let me just get back to this. I feel like I can best explain this. Okay, so chiller, I'll have to do like a little deeper dive to see if it comes on, if it's purely just on outside air temp and not outside air temp. But there should be some kind of like an interlock where the chiller is scheduled, or it comes on based on demand, based on cooling valve position of the air handling units. The most ideal thing that you would want is, which I've set some plants up before like is this cooling valve needs to be open some percentage, like 15%. Both air handling units need to have cooling valves open, maybe even 25%. So at that point in time, the air handling unit would be in economizer plus cooling mode, and we'd be completely maxing out economizer free cooling. This valve would be open, some interlock of like 20% or something, and then we bring on the chiller. And I think what's happening is like this, they're not interlocked, and that's what's causing the this is just a hunch here, that the chiller shuts down on its own operating schedule and it's not looking to see if the air handling unit is still running or calling for cooling. This is a hunch. So we have 70 hours, which could be directly inputted into some kind of equation for energy savings. I'm not paying too much attention to this mixed air temp below outside air and return air. I kind of wanted to zero in on this. Okay, so fault equation 8 by guideline 36. I have to start wrapping this video because it's going kind of long. Fault equation 8 is supplier temperature mismatch in economizing mode. It says that we have a fault here. Economizer open, so I think I need a way to like I need to write this a little bit better. Because we do have it's not shown here, but when this damper is open beyond its minimum position for ventilation, that's when we're just saying the economizer is open. I think it's just defaulted to like 40% or something like that. Economizer is open and chilled water valve is less than 10%. So that means that we're just free cooling. And we're saying that the supplier temp minus basically the supplier temp and the mixer temp should equal each other. This makes me think of something. I think we might have to just change briefly how this fault equation is written. Let me just open up guideline 36. Something doesn't look right. Okay, so let's just scroll through guideline 36. Stupid little mouse tool. You open it back up. Mouse highlighter. Okay, there we go. Okay, this is the operating states that I was talking to you about before that defined by guideline 36. And let's look at fault condition 8 right there. Supply and mixer temp should be approximately equal. Okay, so something doesn't look right the way that it is written. So this is supplier temp average minus this delta temp for the supply fan minus the mixer temp. So basically, it's the supplier temp minus the fan heat should almost equal 0. And it's like a really fancy way of saying that supplier temp and mixer temp should be approximately equal, and this is like a really fancy mathematical way of saying that. And then this guy is just delta temp for fan heat, which is usually you do get a degree or 2 off of the fan motor. See, I just wanted to validate that this parameter here for fan heat, temperature rise across the supply fan is 2 degrees Fahrenheit. That seems more correct. 1 degree C, 2 degrees Fahrenheit. And then for here, we are hard-coded as 0.55. But this might be an adjustable parameter. Let's just look. I'll have to put this, let's make this an adjustable parameter and default it to what Guideline 36 recommends. I don't think it'll make a whole lot. Not to, it won't make a huge change here, but okay, so FC8. Oops, I'm gonna title this it's Liberty 100 building 7-16 GL 36 F fault condition 8. Need to have an adjustable parameter for the fan heat. You see, got that noted. If anyone else is trying this out, just use your GitHub account, create a GitHub account, and then just start GitHubbing stuff you find wrong. 312 fault hours. Okay, so we just have to drop down. Shoot, another one we should look at next is fault condition. These fault conditions 8, 9, 10, they're all to do with free cooling. Oh boy, we have a lot of data to look at here. So faults, bool. So this is, I think, fan status. Okay, so we have outdoor air dew point on here too, which I wanted to view. So let's just zoom in on the fault. So kind of early in the data when it would be nice and cool outside. Okay, so we have fan running, which is good. We're only flagging faults when the fan is running. Oh, this is air handling unit 2 with this really weird duct static pressure issue. Man, what the heck? Oh, 2. Oh yeah, you're in unit 2. Okay, we'll have to look at this on both 1 and 2. But let's just zoom in here. Okay, so if we have a confirmed fault, And basically we want to see that the, I forgot what it was, mixed air temperature should be approximately equal to supplier temp. Jumping around here a bit, 2-bit. All condition 8. Supplier temp and mixture temp should be approximately equal. We have outside our damper. Those look pretty damn close to me. So this is just something that just needs to be tuned. Discharge air temp, and like that's perfect. 2-degree rise across the fan, just like what Guideline 36 would recommend. And we do, oh, this is fan. Where is our outside our damper? Ooh, 100% open. Nice. So this is perfect. This is exactly what we'd want to look for, is that we're in 100% outside air mode. Fan, it maintains. Duct static pressure is maintained. 59% speed, and we have 100% free cooling going on right there. And we have a 2-degree, we're maintaining 57-degree mix temp, 59-degree discharge, and let's just see if we're actually cooling using mechanical cooling here too, and not even using any mechanical cooling. This is like what we want to look for. Must be like just a little bit of mechanical cooling towards the end of this day, but so this will be a tunable fault. Okay, so we just have to maybe, which looks good to me. Let's look at this guy. Let's look at fault condition. Oh, that was fault condition 9. Outside air temperature too warm for free cooling. Oh, that's what this was. Sorry, I was looking at the wrong fault. Outside air temperature too warm for free cooling. Let's look at outdoor air temperature. And then I have dew point on here too. Let's get rid of this, all this other stuff. Seems like some kind of something's not right here, because this looks like excellent weather for excellent conditions for free cooling. So like our dew point is way below 60, and our outside air temperature is only 53 degrees. Okay, so we have something wrong here. This is I'll have to look into this. Calculating faults. Data was confirmed. It's proper. So okay, so like I will look into this, because this is exactly what we would want to. Let me just see. We're definitely on fault condition 9, confirmed fault. Why would this be flagging a fault? Let's just look at Guideline 36 for outside air temps too high for free cooling without mechanical cooling. Okay, so if we go into fall condition 9's equation, so outside air temperature average minus the air threshold, their supplier set point. Looks like a funny one. Outside air temperature average minus the air threshold is greater than the supplier set point minus this fan heat and the supply air. Okay, so this is a funny one. I have to think about this. So outside air temperature minus, so this will just be some, what is the supplier temperature set point? I have a feeling we might be coming back to this one tomorrow because I am plumb out of time. Let's look at this. Get rid of that. Let's look at the dupe. Get rid of that too. Okay, so outside air temperature, discharge air temp set point is 48. So this is, yeah, this really cold unit. Okay, so this is probably screwing up the equation. So the discharge air set point is 48 degrees, which is something that we've flagged as being kind of odd already, is having a really low discharge air temp set point. So it's causing this fault equation to get screwed up. So right here, the outside air temperature is 58 degrees and the discharge air set point is 48, but the, let's look at dew point. Yeah, you're like well within. So the air handling unit is in 100% outside air mode, and I'm gonna ignore this. This is doing exactly what it's supposed to be doing. The thing that is just like really odd is that the discharge air temp set point is so low. Like we talked about, there's other unknown mechanical problems in the building that we just don't know why they need to have such a low. Okay, so let's just look at one of these other. There's other economizing. Economizer tamper stock. So maybe I'll have to look at this too. We do have a few more economizer equations. Here's another economizer equation. Economizing when outdoor air is unfavorable. Outside air temperature is greater than 53. This needs to be rewritten for dew point if we have it. Okay, so I would kind of gloss this over again. We do have kind of some funny, the way that these rules are written, there's not enough tunables on the side, and I like to go off of this outdoor air dew point concept below 60 and the dry bulb being below 72 in degrees Fahrenheit as being kind of like this web weather station way of like saying we could be economizing off of outdoor dew point. So I'll be kind of refining some of this. So this is all I have for today, guys. Hopefully you're liking it, and I will see you guys on the next one.